Section 8.6, using the Clausius-Claypeyron Equation to calculate the vapor pressure as a function of temperature. Well, is it possible to make water boil at the room temperature? Yes, of course. You lower the pressure to 0.03 bars, then you can boil water at 25 degrees Celsius. We'll prove it. Again, dP over dt is delta S over delta V, and delta S is delta H over T, so we have this equation for the vaporization. Right, and then we make approximations. The change of the molar volume is the molar volume of gas minus that of liquid. Approximately, it's just the molar volume of gas because the molar volume of liquid is negligible. And then we use ideal gas law. This is simply V over N. V over N is RT over P. We plug in RT over P in here, we get this equation. And if you look at this equation, we're going to assume this enthalpy of vaporization is roughly a constant. And then we'll solve this differential equation. So first, we move things around. We have T and T being combined. We move this P up. And then we have dP over dt, okay? And then we move all those pressures to one side. The other variable temperature on the other side, we have this equation. How can we solve this differential equation? We simply integrate both sides. We integrate this dP over P. We integrate this dt over T squared. We assume this delta H vaporization is constant. Why can we do that? Actually, the enthalpy of vaporization does depend on temperature, but the dependence is small. Why? The dependence is delta CPM. Delta CPM is the CPM of water vapor minus the CPM of liquid water, if we're talking about water. Okay, and this delta CPM is typically very small. If you integrate that, it's typically very small. Let me use water as an example. The enthalpy of vaporization of water at 100 degrees Celsius is roughly 40.7 kilojoule per mole, or roughly 41. At the room temperature, it's roughly 43. So 41, 43, there is some change, but the change is small. The reason we want to treat this as a constant is because it makes our job easier to integrate the both sides. Well, of course, I mean, somehow if you want to be more accurate, you can write this as a function of temperature, and then you just keep this inside the integral. You integrate this function of temperature carefully. But if we can assume the enthalpy of vaporization is a constant, and in most cases we can, and then we can integrate this both sides, we get the logarithm of P2 over P1 is equal to negative enthalpy of vaporization over R times 1 over T2 minus 1 over T1. So the boiling point of liquid is always higher at a higher pressure because this is always positive. Okay, if T2 is greater than T1, all right? If T2 is greater than T1, this is negative. If this is negative, this whole thing is positive. And then P2 is greater than P1. Again, if T2 is greater than T1, this is negative, this is positive, this is positive. Negative, negative is positive. Therefore, P2 is greater than P1. Now let's look at one example problem. Let's look at water. Let's look at the boiling point of water. Given the external pressure being very low or very high. So we're going to calculate the boiling point of water under a 0.03 bar condition or 2 atm condition. What does that mean? That means if the external pressure is 0.03 bars, very low pressure, as long as the water vapor pressure reaches 0.03 bar, it's a boiling point. It's a boiling point. Water can form bubbles inside the liquid. The bubbles can come out and form vapor. So that's the boiling point. Or we can increase the external pressure so that this water vapor pressure will have to reach 2 atm. For the water to boil. It's more difficult. You need a higher temperature. The enthalpy of vaporization of water is 40.65 roughly, and then we're going to do the calculations. So this is P2, this is P1, this is 1 over T2, this is 1 over T1. So I plugged in the enthalpy of vaporization. Okay, you can plug in 41, 42, 43. The result is not going to change that much. And over here, this is R. And I'm doing this control click. Hopefully I can show you how to use Wolfram Alpha to do the calculation, because I'm too lazy to even use a calculator. Alright, I just type this up, I get the temperature. Alright, I get the temperature. Okay, where's the temperature? Okay, the temperature is here, 294. This is 21 degrees Celsius. So under 0.03 bar pressure, water boils at 21 degrees Celsius. You can put your hand in the boiling water. Alright, at 2 atm, similarly, we just change the pressure. So this is 2 atm, this is 1 atm. Okay, so, oh, by the way, I'm using bar here and bar here. For convenience, I'm using 2 atm here and 1 atm here. This is 1.01 bar, which is 1 atm. This is also 1 atm. Alright, and then you do this calculation. Honestly, you just need to click this link and replace some numbers. And then you get 394. Okay. Well, this is actually 121 degrees Celsius. So 21 degrees Celsius higher than the normal point of water. That's why you need to buy a high pressure cooker if you want to cook something on top of Mount Rainier or on top of Mount Everest. Mount Everest. You need a high boiling point. You need hot water.